Alright, hell yeah. So we have linear algebra, and today we're going to go over LU factorization. Booyah. And we're just going to get right into it. The general gist is that we have AX is equal to B. These are matrix vectors. We have our coefficients over here, this matrix A. This kind of represents like your X, Y, Z, W. And this matrix X is your X, Y, Z, W. And so that's going to be equal to this list of constants over here. And we want to find what X, Y, and Z are. And at the end of the day, these are just equations. These are four equations, where the first equation is 1x plus 2y plus 3z plus 4w is equal to negative 10. That's equation 1, and you could do that 3 other times. Essentially we just have 4 equations and 4 unknowns. So so go do it old-fashioned. The whole reason we're learning linear algebra is because maybe you have 5 equations, 5 unknowns, 10 equations, 10 unknowns, 100. Sky's the limit, and doing it from a hand combat, hell no. It just ain't gonna work. So, all right. So we use this LU factorization, and you have to use Gaussian elimination anyway. At the end of the day, if you got this to have zeros here, you're kind of like, well, it is basically the solution vector, because we just have A is equal to X, and we're going to call this X, Y, Z, W. And then just straight across, this is 63W is equal to negative 243. You could do that one. W is just this divided by 63. Once I know W, this is just negative 494W. Get it to the other side. And then and this is 47z, so divide that by 47. And then so it's just like, why aren't we doing it that way? The reason is because maybe you have a linear system where like these values are always going to be the same, but these values could change, and I want to put different inputs. And I would have to go for every vector of constants over here, B, I would have to do that whole Gaussian elimination process, which is lengthy. It still is relatively simple. But check this out. If we do have AX equals B, I basically want to divide by A both sides, and that just gives me, It would give me something like that. You can't divide matrix, but you can multiply. Dividing, if I had 2 divided by 2, that's the same thing as 2, inverse 2 times 2. And so, 2 divided by 2 is 1. Inverse 2 times 2 is 1. And so that's what we have. We have inverse of matrix A times matrix A is equal to the inverse of matrix A times the vector of constants. And then, hell yeah. And what we say this is equivalent to 1. We're gonna call it an identity vector. So it's still a vector times our solution vector, but at the end of the day, it's like it's essentially just like having this vector of solutions X, Y, Z, W is equal to, and then this vector inverse is still going to be a 4 by 4, so we're going to have a 4 by 4, but this is a 4 by 1. And so how do we multiply vectors? Well, it's this, this, this. Think of these as like 4 equations, but we didn't need to have 4 equations. You could have just had 1. But each equation's got 4 things going on. And then so in this, you have to have 4 rows to represent those 4 things. And so that's what we have. And so that's just vector multiplication. Once we multiply, whoops. Anyway, and I think we just need to move on. But hell yeah, and then you get just a row of solutions, 4 solutions to that. And so in that process, if I know, so what did we do? We took this, multiplied by the inverse on both sides. This essentially turns into 1, and then we just have the inverse of A times B. And then all we have to do is just take these take inverse A multiplied by B. In that order. You got to do it in that order. And then you're just going to get your answers. So all you have to do is just like that, 4 times, and you're good. So then you can have any values here. You can change those values. So once you get inverse A, then you're king, and then you're just good to go. So that's the reason why you would do LU factorization. All right, hell yeah. All right, now this video, I want to go through the process of like how I'm currently doing it. Because to get the Gaussian elimination, you're first going to get, you're going to get a 0 here, a 0 here, a 0 here, a 0 there, and then a 0 there. So that's kind of the technique. What you can do with equations is, just like if I have 2x plus y is equal to 4, and then I have x plus y is equal to 1, I should have done it the other way. But I can just multiply this whole equation by 2 on both sides, right? So this just should be 2x plus 2y is equal to 2. And then you can see how that, well, no. And then so I can do that. And then if I had that, I can subtract equations, and I could have, the 2x's cancel, and then I have 1y minus 2y. So that's going to be negative y. 4 minus 2 is 2. So sweet, y is negative 2. So that's kind of the process we can do that. And then I can still, after I did that process, I can, I got down to right here. So these two equations could be represented as 2x plus y is equal to 4 and just negative y is equal to 2. From the original equations that I had, these are two equations that are totally similar. Hell yeah. And oh yeah, that tripped me up for a second, just because, I mean, these two, if we plotted these as lines, like these lines look totally different now, but they're still, their values, the solutions to these are still remaining the same. Okay, so what we're going to do, or how I do it, and I think how the textbook does it, like we want to multiply row 2 by something. And so we do this. I'm going to say row 2 star, because it's going to be the new row 2. Is going to be row 2, and I want to do plus. Here we did subtraction, and that's a good way to think of it. But I'm going to say add the opposite. So I'm going to take row 2, and then I want to take row 2, and then I want to add it. I want to add it a multiple of row 1. So if I multiply row 1 by negative 17. Cool. Row 1 becomes negative 17, negative 34. And this is where I'm going to use my calculator. Negative 17 stored as x, and then we have x, 2x, 3x, 4x. So we have negative 34, negative 51, and negative 68. Cool. I'm going to take row 2 and then add add negative 7. I'm going to add basically that, which is negative 17 times row 1. And hell yeah. So row 2 becomes 17 plus negative 17 times 1. And then it becomes 22 plus negative 17 times 2, and then we got 27 plus negative 17 times 3, and then we have 8 plus negative 17 times 4. Cool. And, I mean, to make less mistakes, I would use a calculator to do this. I would say, hey, here's row 2, I'm modifying row 2. I'm going to go 17 plus the multiple, and I'm going to say negative 17. I'm going to store that as my as x, just for convenience. So I'm going to go 17 plus, and then just 1x, and then I'm going to go 22 plus, well, x times 2. And then I'm going to go 27 plus x times 3. And then 8 plus x times 4. Hell yeah. So these values become 0, negative 12, negative 24, and negative 60. So now I can replace this portion of the equation with those values. Alright, hell yeah. So now I'm going to show you kind of how to, like, I would do the first step in my head, because what are you going to do? You're going to write these, like, 1,000 times. And so I'm going to write the top row. And then I'm going to modify the next row. I'm at least going to write the modification of the next row. So this becomes 0. And then I would just, I would say 17 17 plus negative 17 times 1 is 0. And then I would go 22 plus negative 17 times 2 is negative 12. 27 plus negative 17 times 3 is negative 24. And then 8 plus negative 17 times 4 is negative 60. Okay, so we're beginning to get the upper matrix. At the same time, we want to be building the lower matrix. So the lower matrix, if this is the upper, this is going to be the lower. The lower matrix will start with the inverse matrix. And then what did we do to this value right here? I mean, what did we do to row 1? We multiplied, we used that negative 17. So we modified row 1 by a multiple of negative 17. So we're going to put here the opposite of that. So 17. Cool. And with any of these little tricks, you know what I mean? Like, I don't know how to prove that. I'm just walking myself through the steps. But once we get our upper and lower, what this says is that A is equal to LU. A is not equal to UL. So I once I get this upper and lower, I actually, it would be better to actually put the upper on this part of the page and the lower over there, so then I don't have to write them again, so that I'll try to do that next time. Because matrix multiplication for most matrices is not commutable. I'm not going to try to say that word again. I'm going to mess it up. But like how you commute to work, you know what I mean? I commute to work going this way. Going back, I don't go home. You know what I mean? If this is home and this is work, cool, I can go to work. If you try to go the other way, do this first, you know what I mean? You're just in a different location. So it's not commutable. See, I don't know how to say that. All right, so the next row, I got to take row 2, which is 77. I want to make a 0 here. So sometimes just like, hey, but I'm going to be 77 plus what times 1? Well, negative 77 times 1. Cool. So I'm going to multiply row 1 by a negative 77, and then so 77 goes right there. And you can see, well, this next one should be negative 10 just by observation. All right, so let's do this. So we have, and that's where I do negative 77 stored in my calculator as x, because I'm going to go 77 plus 1x, and then 44 plus 2x, and then 47 plus 3x, and then negative 494 plus 4x. Now, at any portion of this game, I could make mistakes. And I do not like this problem because I made, see, I'm already making mistakes. So let's go down one. This is 0, negative 110, negative 184, negative 802. All right, hell yeah. Okay, so and then the next one, I'm going to multiply row 1 by a 10. So 10, I'm going to store that in my calculator. And then so we have negative 10 plus 1x, and then we have 1 plus 2x, 7 plus 3x, 63 plus 4x. Hell yeah. So now we have a 0 here, 21, 37, 103. Okay. Our first row had a 1 in it. Now this row has a negative 12. To get this to be 1, I have to multiply. I either have to multiply by a negative 1/12, you know what I mean? Or multiply by 1 divided by negative 12. You know, just divide by 12. But that's the value that I'm going to be multiplying. If I multiply this row to get this to be 1, which I'm going to do, I have to come over here and do the opposite. So if I divide by 12, if I divide by negative 12 right here, I have to multiply by negative 12. You know what I mean? So if this is the value, what's the inverse of this? It's just flipped. And that's the same thing as negative 12 divided by 1, which is negative 12. So I'm just going to put a negative 12 there. That's what happens there. This row, I got to divide negative 12 by this entire row. So we have 2, and this becomes, negative, 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 divide by negative 12 everywhere. See, I almost made a negative mistake. These are all going to be positive, and this is positive 5. 5 times 12 is 60. Now we can do that same process. Negative 110 plus a multiple of this row is going to be 0 right there. So, well, it's going to be negative 110 times 1. Hell yeah. So I'm going to do negative 110, store that as just a variable in my calculator. And now right here I'm going to go negative 184 plus 2 times that variable. So negative 404. And we have negative 802 plus 5 times that variable. And we have negative 1352. That's the other thing about this problem. Not super nice numbers. Okay. And what did we do? What's our variable? Negative 110. So I'm going to put the opposite of that. I'm going to put 110 here. And maybe that's not right. Oh, completely not right. So yes, I'm glad I did that. Because let's go back to the first one. If I put negative 110 in my calculator and I did negative 110 plus 1x, hell no. So my variable has to be 110. And if my variable is 110, the opposite of that is a negative 110. So hell yeah, we just caught our first error, which is pretty sweet. Alright, so I have in my calculator, I just need to be 110. And let's not use that variable. So I have negative 110 plus 110 times 1. Cool. And then I have negative 184 plus 110 times 2. This is 36. And then I have negative 802 times 110 times 5. See, and I probably made a mistake here as well. I just kind of feel it. Don't you feel it? No, this value is crazy. But I just messed up. This has to be add. So I'm taking negative 108 plus 110 times 5. And so we have negative 252. But yeah, that's a bummer. The second you start making mistakes, your paper gets a lot tighter. So sometimes what I do is, like, if I'm kind of done with the answers, I'll circle them. Alright, sweet. And yeah, negative 184, I just want to check that one. Plus 110 times 2. Yep, perfect. Okay, so we want to get this value. I'm going to multiply this by a negative 21. Because I did that, this value is going to be the opposite of it, 21. Negative 21 in my calculator. I'm going to go 21 plus 1x. Cool. 37 plus 2x. and then 103 plus 5x. Hell yeah. So I get 0, negative 5, negative 2. Alright, hell yeah. And at any time, we could be making mistakes. And when's the first time do we get to check our mistake on this? Well, I would say it's once you get your upper and then your lower, and we're getting them at the same time, and then we're going to multiply the lower by the upper, LU, and then see if we actually just get this matrix. And I don't know, yeah. I mean, I'm saying probably we messed up somewhere. So I'm going to divide this by 36. Because I divided it by 36, I got to multiply this by the inverse. I mean, if I did 1 times 36, if I multiplied this by 1 divided by 36, the inverse here is 36. Cool. So this becomes 1. Negative 252 divided by 36 becomes negative 7. And now I think I'm on board. And so we have 1 here, negative 7 there. These are probably all final answers. And remember how if we get tight, I was just saying if you circle those, they can pop more. And so actually I shouldn't have circled the 36. We're literally done with that one. This is a 1 now. We already divided by this by 36. Cool. And then so here's our values downstairs. I mean just in this last row, negative 5. I want to make this a 0. So negative 5 plus 5 times this row. 5 times 1. Cool. So 5 stored as x is my variable, and I'm going to go negative 5 plus 1x, and then I'm going to go negative 2 plus negative 7x. So this becomes 0, done with that, and this becomes negative 37. Hell yeah. And what did I multiply here? What's my variable? 5. And so the opposite of that is negative 5. And that negative 5 should actually just, be this negative 5. And so we're good. Negative 10, the 21, that checks out, and all the others. And then check it out. So here is our upper and our lower. So we're done. That could have been a video in itself. But I mean, we just started, baby. I mean, that's just the tip of the iceberg. So hell yeah. Alright, I took a little break, but we're back, and booyah. So I have written the lower and the upper. This was our original A. And now we can do our first check. We want to make sure that the lower times the upper matrix is A, because that's what we're trying to say. We're saying we're going to take matrix A, and we're going to separate it into a lower and an upper. A lower triangular matrix, that's what that's called, and this is an upper triangular matrix. And when multiplied, the lower times the upper, you're going to get that original matrix A. Cool. So, hell yeah. How do you multiply a matrix? It's start with a row and then a column. Now, and then what's our output? Because we have 4 rows, so our output is going to be 4 different rows. If we were just multiplied this by this, you know what I mean? We can do it because, this is an x, y, z, w coordinate, and then you need to multiply. So the second matrix has to have this many rows. So even if I just have one row with 4 columns, this one column has to have 4 rows. Cool. And that would give me one value. If I had 2 rows and then 1 column, I would get 2 values from my solution. And so we have 4 rows. And so if I just had this one column, I would get 4 different values for my solution. But now I have 2 columns. If I just had 1 row and 2 columns, I could do this row and this column to get the value. And then I could do that same row and then another column to get another value. And so if I just have 1 row, I'm still going to have 1 row of values, but I'm going to have 2, 1, 2. Cool. And then so therefore, and if I had 2 columns and 4 rows, 2 columns of values and then 4 rows of values. I have 4 by 4, so our output is going to be a 4 by 4. Hell yeah. And so this first one is going to be this row in this column. 1 times 1 plus 0 times 0 plus 0 times 0 plus 0 times 0. So hell yeah, 1 times 1 is 1. Anything multiplied by this first column. So if I say, you know, if this times this is equal to this, we'll just bring it down here. Then I want to find this first value right there. That's going to be this row in this column. So that's 1. All right, how about this value? That's going to be this first row multiplied by this second column. That's going to be 1 times 2, and then we have 2. And you can kind of see that this value right here is going to be that first row, third column. And we're going to multiply by like this. And we get 3. This value is going to be this row in this column. Because of all these zeros, we're just going to have 1 times 4. All right, the next one, let's see if it gets any trickier. What's the value right here? It's going to be this row and this column. All right, we got 3 zeros, so this is 17. And then so if I move on to this value, we're going to have that same thing. It's going to be this row and this column. We just have a 1 there, so it's going to be 77. And then this one is going to be negative 10. All right, how about this value? It's going to be this row in the second column. So 2 times 17 minus 12. Okay, so let's do that in our calculator. 2 times 17 minus 12 is 22. How about this value? Third row, second column. 2 times 77 plus 1 times, and maybe how you would say this, I mean, we could say it's 77 times 2 plus negative 110 times 1. Sometimes if just one of the numbers is lower, I think it's easier to say 2 times 77 than it is to say 77 times 2. All right, and that value is 44. All right, let's check this value. 2 times negative 10 is negative 20, plus 21 is 1. All right, we're doing pretty good. And then so how about this? Well, we already did that one. How about this value? So it's going to be second row, third column. 17 times 3 plus negative 12 times 2. And then, so we're doing third row, third column. And then we have 36 times 1. Oh, whoops, I'm not even... There we go. Pull it up again. Plus 36 times 1. And then 0 times 0. Plus 0, 0 times 0. So we get... oh, and we probably messed it up. Well, let's see if we did. 77. Yeah, we did. This should be 77, not 17. 77 times 3. Oh, yeah, let's just do that one over again. It got messed up in my calculator. 77 times 3 plus negative 110 times 2 plus 36 times 1. Cool, we get 47. On a roll. All right, how about this value? Negative 10 times 3 plus 21 times 2 plus negative 5 times 1. And we get 7. All right, sweet. So we only have three more to do. It's going to be this third row, fourth column. So we got to do them all. So we got 17 times 4 plus negative 12 times 5 plus 0 times negative 7. That's just 0. Plus 0 times negative 37. Cool. So we get 8. Hell yeah. Now this one, third row, fourth column. I mean, to get this value right there. So we have 77 times 4 plus negative 110 times 5 plus 36 times negative 7. And then 0 times 0 times negative 33 is 0. Hell yeah, so we get that value. Okay, one more to check, and I think we're good to go. So we have negative 10 times 4 plus 21 times 5 plus negative 5 times negative 7 plus 1 times negative 37. And even today, I got good at just using the calculator like a keyboard number pad, because there's so many little calculations that just made it so much better. Okay, so we officially have our lower and upper. You know what I mean? Because when we multiply this matrix by that matrix, we get A. Now, it just it reminds me, or I'm just thinking, like, is this the only two matrices you can multiply together to get A? Or mainly, is if, let's say I got the upper right, is there any way that we could modify this matrix and still have gotten A? You know what I mean? I don't know. I would assume... yeah, I don't want to answer that. I don't want to definitively say no, they're singular. But anyway, hell yeah, let's move on. All right, hell yeah. So the next stage. So now we're done with that stage. The next stage is to take each of these matrices and find their inverse. I want to find inverse L and then inverse U. And so what is the definition? The definition of the inverse. So if I just have inverse of A, that's going to be 1 divided by the determinant of A times the adjoint of A. No one knows what the hell of adjoint is. Maybe you know what the determinant is. So, and this is going to hold for, if I want to find the inverse of the lower, 1 divided by the determinant of the lower. Sorry, just 1 divided by the determinant of the lower. The adjunct is the cofactor transposed. And what is the cofactor? The cofactor is the minor with, and it might be a negative. So it's a negative 1 I to the I plus j times the minor. That's the cofactor. All right, so let's kind of walk our way through that. So what I like to do is just find the minor first. So that is going to be, so the minor of this matrix is the minor of every location. You know what I mean? So I have to put my finger right here and be like, what's the minor? The minor means that we're going to cross out this column and this row, and the remainder of this matrix we have to take the determinant. So maybe the first thing to do is actually do the determinant of A, because then we can introduce what a determinant is, and then the determinant of this matrix, because if we're trying to find inverse of the lower, that's going to be 1 divided by the determinant of the lower times the, and I'm just going to say the transpose of the cofactor. So the determinant of this is pick a row or a column, and then whatever value you have, let's say 1, I'm going to take 1 times the cofactor of that location. Cool. So the cofactor is the minor at that location, and then with a sign change of depending on what row and column that value is in. That's in the first row, first column. So this row and column is going to be a positive 2, and there is no sign change. So there is no sign change for this first diagonal because we have 2 and 2, 3 and 3, 4 and 4. There's no sign change for this diagonal and this diagonal. This one and this one. The opposing diagonals, this one is going to have a sign change because we have row 2, column 1. I is 2, column j is 1, and that's going to be a 3. Negative 1 to the 3 is a negative 1. Okay, so to find the determinant, you have to take this value and then multiply that by the cofactor at that value. And then we're going to add it to the cofactor of the next term, which is 0. The value of 0 times the cofactor of that location, plus this value times the cofactor at that location, plus this value times the cofactor of that location. Because these are zeros, and that's the benefit of doing the upper and lower matrix, you are just left with 1 times the cofactor of this location. So the cofactor is the minor, and the minor is get rid of this column in this row and take the determinant of the remainder. We can do that same process. We have a 1 down here, which is, we'll just use this row. So I'm going to say, I'm going to take the determinant of this is the cofactor of this. So it's 1 times the minor of that. And then with the sign change, there is no sign change. So after that, you know what I mean? We have, again, we have 1 times the cofactor of this location. Instead of think cofactor first, just think minor first. So we have the minor of this, so we have 1 times the minor of this location, which is the determinant of this new 3 by 3. So we're going to do that same process. I'm going to choose this row, these 3 values. And I'm going to have 1 times the cofactor of this location. The cofactor of this location is the minor of the remainder matrix, and the minor is just the determinant of the remainder matrix. Or the minor of this location is the determinant of, after getting rid of this row, this column, and this row. So hell yeah. Alright, that's brutal to just kind of explain it in a, I feel like it's a horrible explanation. But anyway. So hell yeah, let's walk through it one more time. I want the determinant of this matrix. I'm going to pick this column because it's just going to have 1 times the cofactor of the remainder. The cofactor of the remainder is the same as the minor of the remainder with a sign change if needed. And so, or depending on its location. Cool. So I'm just going to, and then the minor of a location, the minor of this is get rid of these and just take the determinant of this. A 3 by 3, you have to do that same process on repeat. The determinant of this, which is the minor of this location, the cofactor is the sign change. There is no sign change. But yeah, the minor of this location is the determinant of this. The determinant of this matrix, same thing, you have to choose a column. And I'm going to choose this. It's going to be this 1. Cool, that's a 1, who cares? And then it's the cofactor of this location. This location is no sign change. And so it's the minor of this location without a sign change. The minor of this location is get rid of these 2 rows. And what you're left with is this 3. And the minor is the determinant of the remainder matrix. And so now we can see the determinant is just negative 12 times 36 minus these 2 multiplied, which is 0. So brutal. And then, and that's it. That's the full determinant. And then you can see that the determinant was just these 2 numbers multiplied. So that's therefore, is that if you have an upper or a lower, if you got zeros in these locations, because, you know, the determinant is just the multiplication of the diagonals. Hell yeah. Okay, so the determinant is just going to be negative 12 times 36. That's the determinant of this is negative 432. Cool. So the determinant of this is going to be 1 divided by negative 432. And now we need to find the cofactor, the transform of the cofactor of this matrix. But let's put cofactor aside, because the cofactor is the identical to the minor, just with sign changes depending on whether those minor locations fell in this row, this, you know what I mean, these diagonal rows, if you can look at it that way. Or whatever its value, if it's in a 1, 1 location, that's going to be a positive 2, you know, it's not going to have a sign change. So that's what we're going to find, the minor of this matrix. And you have to find the minor of every location. So just an arbitrary location right here is cross out this column and cross out this row. It's good if you can do it with your fingers, even visually. I'm doing it, you know what I mean? And then you can see that the remainder is a matrix, and it's a 3 by 3. So the minor of this location is removing row and column, and then finding the determinant of this 3 by 3. But yeah, the sucky thing is the determinant of a 3 by 3 is, you know what I mean, this value times the cofactor of this location, plus this value times the cofactor of that location, plus this value times the cofactor of that location. Coolness, we just have 2 zeros, so we're still just left with this value times the cofactor. And the cofactor is the minor of that location. without a sign change. So sweet. The minor of that location is just the remainder determinant after we cross out. So we're saying if I'm finding the cofactor of this location, I want to find the minor, no sign change, so that is the cofactor. Minor of that location is the determinant of the remainder. The determinant of the remainder is the this value times cross out. So what do we got crossed out? So we got that, and then and then we're going to cross out this row and column. So it's the determinant of this matrix, which is negative 12. So it's kind of a brutal process, but I would imagine, I don't know, like I just want to be able to do that visually. So so let's go through and hit all the locations, and we'll go back to that one. And we'll see how it worked out. Cool. The minor of this location. Let's block that out. We got to take the determinant of this. I'm going to take this, and then I'm going to find the cofactor. There's no sign change. I'm going to find the minor of that location, which is the determinant of that. So we have negative 12 times 36. Sweet. So this is the minor of this location. Yes. So I'm just doing the minor. Even though when I do the minor of this location, the determinant of this is a function of the cofactor of that location. So sure, I might have to do a sign change. But as long as I choose this diagonal, I probably don't have to do a sign. We'll see if I have to do a sign. Yes, there's a couple places you have to do that. But for the most part, I like to do the minor first because I don't want to worry about all these negatives, switching. Hell yeah. So this location, block out the column and row. And the determinant of the remainder, I'm going to choose this location again. And then so this goes and this goes. And so you're left with those four numbers right there. The determinant of that, 17 times 36. Sweet. And so that is that value right there. Hell yeah. The minor of this, determinant of the remainder, I'm going to choose this. I'm going to choose these, this row to find my determinant. 1. And it's just the cofactor of this row. So row and column get 86th. And now we have 17 times, this one's got two things to do. 17 times negative 110 minus 77 times negative 12. So the determinant of that matrix. Sweet. And we get negative 946. All right, this value. The minor of that location. Now we got something. We got to find the determinant of this. So I'm just going to do this. I'm going to go negative 5 times the cofactor of that location. There's no sign change, so it's the minor of this location. Minor of that location is that determinant. So we got 17 times negative 110 minus 77 times negative 12. Plus, because we're trying to find the minor of this location, that's going to be the determinant of the remainder matrix. The determinant of this remainder matrix is taking, I'm going to use this, this row as my values. Negative 5 times the cofactor of that location, plus 36 times the cofactor of that location, plus 0, so it's just those two. So the cofactor of 36, so it's going to be 36. This is in a negative 1 location, so that's how I'm going to do the sign change, and I'm going to do the determinant of that location. So we got row and column, and then so these four values are the determinant. So we got 17 times 21 minus negative 10 times negative 12. All right, and we got negative 3802. Now, yeah, this is a brutal problem because none of the numbers are nice and they're kind of large. Okay. All right, we got to do one more row, and then I got food on. I don't want to burn it like last time. So, hell yeah. So this location, row and column. Hey, look at that. The minor of this location, erase row and column. And then we're going to take the determinant of the remainder 3. Well, we have 3, 0 times the cofactor plus 0 times the cofactor. All right, hell yeah. So we took a little break, I ate some food, and so now we're back at it. And I'm going to give myself just a little bit more space to work with. That's the bummer about matrix, is like if you don't give yourself enough space. So here is going to be the minor. And so we got 4 values so far. And we'll just try to evenly space these out. See, I feel like I didn't even do a good job here, but kind of crunched in. Yeah, that's the thing. You want lots of paper. So, yeah, let's try to just do this. Get that one there. Just so we feel not so crunched. Heck yeah. Alright, I'm feeling a lot better about that. Okay, now we're just going to continue on with that process. We're going to find the minor of this location. And it's kind of interesting. I don't want to do too much, but a matrix, you know, just in general, is this location is like some sort of value A, and its location is row I, column J. And so this is going to be 1, 1, row 1, column 1, row 1, column 2, row 1, column 3. If it's your first rodeo, I would go out to 3 and then do kind of the dot, dot, dot. This is going to be row 2, column 1, row 3, column 1, dot, dot, dot. I'm not going to get into, well, I mean the fact that this would be row M, column 1. This would be A, row 1, column N. And then the final location would be row M, column N. And you could even say, hey, this is row M minus 1, column N. You could say this is row M plus 1, column 1. Anyway, so hell yeah, you don't have to get too techy. But when we're saying what's the minor of that location, we'll do the minor of location 1, 1. So this new location is the minor of row 2, column 1. And, I mean, matrix is so row, column oriented, and you usually do the row first, then column, so row, column. And it's just good to get familiar with that. So the minor of the value at row 2, column 1 is signified by that. Sweet. Okay, so that's going to be the minor of this location is block out the column and row. And we're going to take the determinant of that. I see 3 zeros, so this is going to be 0. Booyah. Alright, let's do this one. We're going to block out column and row. And the remainder determinant, I could go either way. I could take the cofactor of this and then take the determinant of that, which would be negative 110 times negative 5 minus 21 times 36. Or I could, so I'm finding the minor of this location, so column and row, and I find the determinant of the remaining values. And it's a 3 by 3, so I have to find, you know, I have to take these three values, 1 times the cofactor of this location, plus 0 times the cofactor of that location. Hell yeah, so those two are zeros. And what are we doing? This one. And so I'm going to use this row. And so I'm going to find the minor at this location. Well, the cofactor of this location. And there is no sign change because it's in. If this new matrix had row 1, 2, 3, column 1, 2, 3, this would be in the third row, third column. And then so 3 plus 3 is an even number. And then so the cofactor of this spot is going to not have this sign change. Hell yeah. And it's just going to be the minor of that location. Okay, the minor of that location is block, column, and row. And then so you're just left with 1 times 36. Sweet. So isn't that interesting how if I was trying to find, you know, if I'm trying to find the minor of this location, I'm finding the determinant of the remaining matrix, and I could use those values. If I did that, I would be left with, oh no, I did it wrong. If I use this value, then it would still be 36. So hell yeah. I'm glad I did that because maybe I could have uncovered an error had I made one. Okay, the minor of this location, let's get some more juice. The minor of this location, block out column and row. The determinant of the remainder, I'm going to do, this one was easy, well no, yeah, I got to be careful about this. So I'm going to choose these three to use as my determinant. So 1, I'm going to find the cofactor of that location. It's no sign change, so it's just the minor of that location without a sign change. And the minor of this location is this row, and this gets removed. So we have negative 110. Brutal. But that location, we could have checked a different way. I could use these values to find the determinant. If I use this one, I'm still going to have this row, this column blocked out. And now I'm going to have negative 110. Okay, hell yeah. Let's speed up the process, get a little bit faster. This location, determinant, is going to be negative 110 times negative 521 times 30. Alright, because I made a mistake there, and I guess there's no reason to rush, because if this is all our first rodeo probably. So, the minor of this location, block row and column, find the determinant of the remainder. I'm going to use those three as my deal. I don't know how to say that technically, but it's going to be 1 times the minor of this location, because there's no sign change. I'm going to block that row and that column. I'm left with this 2 by 2 matrix, and it's the determinant. The minor is the determinant of a 2 by 2. Sweet. I see a lot of negatives, so I'm going to now mentally block those out, and it's going to be 110 times 5 minus. So I'm going to do 110 times 5 minus 21 times 36. And we get negative 206. Oh, and I got some jam going. We had some nice jam on toast. Alright, we got 2 more rows to do this, and you can see it's just like, why is this worth it? Because once we do this, then we have to, do the sign change and then transpose. But that's it. Sign change and transpose. But that's just for the inverse of L. And that's only one portion of it. We still got to divide by the determinant, which was just the diagonals. But anyway, that's a lot of work, and then we got to do that same process again. So it brings up the idea of when do we get to check our answer. Well, this is L, and we're trying to find L, the inverse of L. So if I did find the inverse of L, and I multiplied these 2 matrices, it will give me the identity matrix, and then we can check our answer. Booyah. Alright, hell yeah. Okay, so where are we at? We're on this 3rd row. How about we do this one? So I'm going to block these out. I'm going to use, we got a row of zeros, so this is 0. Hell yeah. And, you know what I mean, there's no trick here. We're going to get, this is going to leave us with an upper triangular matrix. We're going to transpose it. We're going to get back to a lower. So this lower, taking the minor and the cofactor of this matrix gives us an upper triangular matrix. But then once we take the transpose, we'll have a lower. Not that it really matters. I mean, I'm sure there's proofs of why that happens. That's the issue with this stuff. Is like, there is proofs of why this stuff is what we're doing. But then you just got to grind it out, and while you're grinding, you're probably forgetting about the actual proofs. And so, yeah, I just want to mention that. Hell yeah. So this location, going to block those out. I'm going to use this value, so those get blocked out as well. Oh, and we got zeros, because this times this minus this times that is 0. Okay, now we should get a value here. The minor of this location, block those out. I'm going to use these 3, and so it's just going to be the cofactor of that, no sign change, hell yeah. And then so once I got blocked this out, I'm going to block this one and that one. So now we're just left with this matrix, which is negative 12. Cool. This one, the minor of this location, Now, it's not the cofactor. You know what I mean? That's why I get confused with minor and cofactor. I get confused with, I get confused with finding the determinant, which is taking this value 0 and then multiplying it by the cofactor of that location, or the minor times the sign change. But we're just trying to find the minor, which is just blocking out that column and row, and then finding the determinant of the remainder, the remaining matrix. I'm going to use those 3, and so I'm going to do 1 times the minor of this location is block out that column and that row. I'm left with those 4. So that's my 2 by 2. Finding the determinant, I see 2 negatives. I'm going to keep that in mind. And then we have a 0 there, so it's going to be positive 60. Hell yeah. Alright, you know what I mean? And it's Blue's Clues. Can you do this before I do it? You know what I mean? The minor of this location. I'm going to block out these. Hey, it's zeros. Hell yeah. Ooh, we're going to get 3 zeros in a row. The minor of this location. I'm going to block out this column, this row. And cool. Oh, 3 zeros right there. Hell yeah. So I'm always looking for that. And this one should be also 0. So the minor of this row is, you know what I mean, do that and that. Booyah. And then we have a column of 3 zeros. Okay, we should get a value. So the minor of this location, I'm going to use the cofactor of that. There's no sign change, so the minor of this location is this column blocked out, that row blocked out. We're left with this 2 by 2 matrix. We have negative 12 times 36. Alright, so we get negative 432. I just want to double check that one, just to make sure. Because I never know, like... Okay, hell yeah, I'm chill. Anyway, but now we can double check. So this, I'm just going to put this aside. This is our... Now, this is not our inverse L, because we just took the minor of it. And that reminds me, yeah, we have 3 different things to do. So right now this is the minor. We need to find the cofactor. The cofactor says this row does no sign changes. This row has a sign change. No sign changes. Sign change. Same thing this direction. Sign change. No sign change. Sign change. Why is there a sign change right here? Because we have row 3, column 2, and we get that property. We get that property where negative 1, I plus j, negative 1, row 3 plus column 2 is negative 1 times 5. That's negative 1, negative 1, negative 1 times negative 1 times negative 1. Those 2 are positive, those 2 are positive, and you're left with negative 1. Cool. So that's why that row changes sign. Alright, let's do it. This row stays the same. This row has the sign change. Negative, positive, negative. This row stays the same. This row has a sign change. The transpose. 2 different ways to do the transpose. Because now this is the cofactor. This is no longer the minor. This is the cofactor. I want cofactor transposed. So what you do is this row I'm going to write in this column. I think that's sometimes the easiest thing, just to not make mistakes maybe. But it's also, the diagonal will stay the same. This row shifts to that row. This row shifts to that row. And this diagonal, I should say row of diagonals. This diagonal shifts to that diagonal. This diagonal goes to there. So you have like, hey, these 2 diagonals switch. These 2 diagonals switch. And these 2 diagonal switch. But I think it is make less mistakes. Alright, hell yeah. I think you'll make less mistakes if you have this row written down this column and then just move on to the next row and do the next column. So let's do it like that. Negative 4, 32, negative 6, 12, 36. See, I'm already, yeah, that's crazy. Look at this. This happens to me all the time. It's because mentally, yeah, it's easy just to get off route. So this row down that column. You know what I mean? And I think it is useful to maybe have stuff to cover up some stuff. There we go. Hell yeah, next one. Next row, written down this column. Hell yeah. Alright, so now this is our cofactor transposed of L. But it is not the inverse of L. So, because the inverse of L is 1 divided by the determinant of L times the cofactor transposed, which is called the adjoint of L. So it's the cofactor transposed of L. We found this, so we would need to take, and so if I just have this, so if this is what we have, we get this upstairs. What we found was the determinant of L times the inverse. So sweet, so just keep that in mind. And the determinant of this one is just, well, we should probably write that. But let's get this. So here is the cofactor of L, which is the determinant of L times the inverse of L. Hell yeah. Which the determinant in our case is negative 12 times 36. So we have negative 432 times the inverse of L. That is what this card is. Okay, hell yeah. So now we're going to double check ourselves, because what I need to do is multiply this matrix times this matrix, and what would we get? So if I do L times inverse L, I would get the identity. That's not quite what we have. We have L times negative 432 times the inverse of L. But I ain't factoring through this negative 432 to get a bunch of fractions. Hell no. So it's best practice to work with whole numbers if you can. Just make sure everything gets up to a whole number if you're able to. That's the sauce. Alright. And then so if I do this multiplication, well, this is still just a scalar where you have L inverse L, which is the identity matrix. So when we do this multiplication, we should just get negative 432, and I'll show you. We're going to get a 4 by 4 matrix that's going to be negative 432, that same value there, and then negative 432. So and then zeros everywhere else. Is basically just, this is the identity matrix of 1, 1, 1, 1, and zeros everywhere else. Times that negative 432. So I just want to stress that. That's very important, is that, you can always factor out scalars. Hell yeah. Okay, let's double check. Hopefully we made a mistake. It would actually be kind of cool to. I don't think we did, because I've already done this one, but I feel like I've made all my mistakes today, and I really don't want to make no more. Alright, let's get some water and chug. Hell yeah. Alright, how to multiply matrices. Row and column, just like this. So always do your finger over and then down, and then maybe at the same time. What I'm looking for always is zeros. I see 3 of them. Hell yeah. And then negatives. I see a negative. So these are the only ones. It's going to be negative 432. And what should I be getting? What the hell did I even just say? I'm trying to get the identity matrix that's negative 432 all down the diagonals, and then zeros everywhere else. Okay, sweet. So, hell yeah. So let's do the next diagonal. It's going to be, And what we're doing is essentially, when we multiply these matrices, I say, hey, is equal to this. I want to find this location, which is this row times this column. What do I see? I see 1 0. I'm going to do this a couple times. Oh, I see 2 zeros. See, they don't pop right away to me. And then so this is the only value, and there is a negative. And so it's negative 12 times 36. Which is that, so we're check Ola on that. All right, this next diagonal, this location, this row, this column. Do I see zeros? 0 at the end, 0 at the start. You know what I mean? Especially when you'll see zeros over here and zeros over there. I always do that. You know what I mean? Look for the zeros first. So the only thing to worry about is this one, and then look for the negatives. Cool. And we're going to get that same thing. 36, negative 12. Hell yeah. Last diagonal is going to be this, this value, this row, this column. A lot of zeros, and then booyah. And then it just spells itself out. Okay, everything else should be 0. Let's check them systematically. Let's see this location. Row 1, column 1. See, I see those 3 zeros, and that 0, everything's 0. This one, row 1, column 1. All right, 0, and then those 3. So hell yeah, now you see a pattern. These 3 knock out those, and this one knocks out that. Okay, now we found the diagonal, so we're going to do these 3. So now this location, 2, row 2, column 3. And I'm pointing to this location, but I should be pointing to this location. That is the value I'm trying to find after I multiply these. What would the matrix look like? Sometimes I do that. That's kind of a mistake. I'm just saying, hey, I'm multiplying these matrices, and I just want maybe just change this value. I don't know. That seems... I mean, visually it just gets, you know, spatially, there's not enough room sometimes. So hell yeah. All right, this row, this column. Do I see zeros? Hell yeah. I see 2 zeros right off the top and 2 zeros on the end. So hell yeah, 0. How about this row, this column? 3 zeros, and this ends in a 0. You know what I mean? And then this one for our final one is this row, this column. All right, 3 zeros in that. Okay, so those were probably the easy ones. Probably get a little harder. We're going to move to these 3. And see what I'm pointing to? I'm pointing to the solutions down here. So we did our diagonal. I want to find those 9 6 zeros. So how about row 2? So row 2, column 1. So I'm going to do this. All right, I see a couple zeros. How about negatives? I see a lot of negatives, and this is a double negative. So I can just think of that as positive, or just be wary. So negative. So I have basically a negative number and then a positive number. Hopefully those add up to 0. So let's just check it out. So I already know that 1 is negative, 1 is positive. I can even just, well, we'll do it thoroughly this first time. We got 17 times negative 432. I'm going to do 17 times negative 432 plus negative 12 times negative 612. That's 0. All right, so the next one. Row 3, column 1. Yeah, a lot of values. We do see a 0 right at the end, but we have 3 values. Do I see negatives? Yes, negatives, negative. So this value is going to be negative. This one's going to be positive. This is going to be negative. Okay, hell yeah. So let's look at our, it doesn't really matter because we can just do it. We can go 77 times negative 432 plus, and then we have negative 110 times negative 612 plus, and then we got 36 times negative 946. Hell yeah. So right now my confidence level is through the roof that the remainder will be good to go. How about that location? Row 3, column 2. So row 3, column 2. And then we got 0 here. See, I'll miss those zeros. And so now it's just going to be, and then we have negative and then positive. And look, those are going to be equal and opposite. Booyah. That's 0. This one. 4th row, first column. 4th row, first column. Oh, we got a lot to do. No zeros. There's a 1 there. Sometimes I look for those too. Negatives, yes. These are 2, so you got negatives. Yeah, so these are going to be a positive. This is my negative. This is positive. And then hella positive. So hopefully I mean, I see negative. No, I see positive, only one negative, and then positive, positive. So this one better be hella big. And is it? 21 times 600. You know, that's going to be another 0 on this. That's going to be 6,000, which is bigger. And then times 2. Okay, yeah, so it's going to be 12, you know what I mean? It's going to be twice 6,000, you know what I mean? It's going to be 12,000, and this is only 3,000. So anyway, yeah, so we should be good. Now we can do it. And you don't even, you know, you can just type in all the negatives into your calculator. Negative 10 times negative 432 plus 21 times negative 612 plus negative 5 times negative 946 plus 1 times 3802. But I think engineers hate this type of work because you lose all sense of the application, or just like it's cool to be able to do the numbers and get the right answer, but man, is it just, it's labor. You know what I mean? And we get the right answer. Booyah. All right, and which one did we even do right there? I'll have to you know what I mean? We did that one. Okay, we got 2 more, I think. So, this value is 4th row, 2nd column. Cool, I see a 0, so it's just these. So we have 2136 plus negative 5 times 110 plus 1 times negative 206. And we get 0. Booyah. All right, last one. All right, and this was just a check. You don't have to do this. You can do your checks later. But, I mean, I think it's for your first rodeo. I mean, you're probably going to make mistakes, and so you might as well check. So, hell yeah, 2 zeros. We got negative. And see, I do this all the time. I was going to say negative 60. I was going to look at this, and I already made that mistake before, too, today. So that's why I look for zeros. Look for negatives. Or look for zeros first. That whittles it down to these two. Look for negatives. Alright, a lot of negatives. This is positive 60. This is negative 60. We did it. So now this is officially the inverse of L times the scalar of negative 432. Hell yeah. So we're going to set that goal aside. Now we're going to do that same process for the upper. I'm going to take a little break. Alright, hell yeah. Alright, now what do we want to do on the upper? Well, we're going to say that the inverse of the upper is going to be 1 divided by the determinant times the cofactor transposed. The cofactor transposed is, what is a cofactor? Well, it's a minor with some sign changes, depending on the location of the value we're taking the minor at. And, sweet. So the determinant, you know what I mean? And let's go back to what a determinant is. It's going to be, I'm going to pick pick somewhere. And I think it can be any row or any column. It doesn't have to, it could be this row. Doesn't have to be a particular, but any row, any column. I'm going to pick this column. And I'm going to use those values. So it's going to be 1 times the cofactor of this location. There's no sign change, so it's just the minor of that location with no sign change. It's the minor of this location times positive 1. And then these will be 0. So it's 1 times the minor of this location. It's just the minor of this location now. What the hell is the minor of a location? It's the determinant of the remainder after you cross out this column in this row. And that's it. So we're on the road to find the determinant, and now the determinant is just the determinant of this remaining matrix. Hell yeah. Now, how do I find the determinant? I pick any row or column. I'm going to choose this column. It has 3 values. 2 are 0. So the determinant will just be 1 times the cofactor of that location. It's in row 1, column 1, negative 1 to the I plus 1 to the I plus j. That's going to be negative 1 to the 1 plus 1, which is negative 1 to the 2, which is positive. So the cofactor of this location is just the minor of this location times positive 1, which at the end of the day is just the minor of this location. And and we're finding the determinant taking those values. So 1 times the minor of this location is just the minor of this location. Sweet. What's the minor of a location? Well, it's when you block out a column and a row. And then find the determinant of the remaining matrix. Cool, now we have a 2 by 2 matrix. And that's literally the proof of the determinant. You do that process until you get a 2 by 2. And the only way this proof works is if you have a square matrix. If you ended up with something like that, get out of town. So you have to start with a square and end with a 2 by 2. And so the determinant of this entire thing, because these were 1 and 1. If these were different values, we would have multiplied, them. And so for this, it's not a good justification for after, once I say the determinant of this is just 1 times negative 37, because that's going to be 0. And so what we find with any upper or lower matrix is the determinant is just the multiplication of the diagonals. But I think that was at least a visual walkthrough of why it's the multiple of the diagonals. I think I will get better at telling you what the proof is, but I think those are for separate videos. One, we just want to use the applied methods, but we don't want to get too too just hand wavy to be like, oh yeah, I just multiply the diagonals every time, right? Well, only if you have an upper or lower, and that's the reason, because you should be able to see it. If you have an upper or lower, you're just going to take that value, which could be 10 times the the minor, and then that's going to be, and let's say this was 5, so then it's going to be 10 times 5, times 1 times negative 337. So that would be the multiplication of the diagonals. All right, hell yeah. So yes, the determinant of this one is going to be negative 37. So that's one part of finding the inverse of the upper. 1 divided by the determinant of the upper times the cofactor transposed of the upper. But yes, I don't like to find the cofactor transposed right off the bat. You could. Do you want to do both? I think it's a good practice. Let's do the cofactor transposed, and then we'll double check it with the minor. So this is going to be the cofactor transposed of u, and this is going to be the minor of u. I think sometimes it is useful to practice 2 steps at once. Anything transposed, this diagonal will not shift. So let's just start with the diagonal. The cofactor of the first diagonal doesn't have a sign change. 1, 1, 2, 2, 3, 3. I'm just mentioning the I and j components. The I and j location is always positive. So literally, the cofactor of the transposed of these diagonals is just the minor of those locations. The minor is cross out column and row. Find the determinant of the remainder. I'm going to use those 3 as my, I'm going to use that row as my whatever the thing says to do. But hell yeah. So 1 times the, so hell yeah. So it's just 1 times the determinant of this. So this first value is negative 37. Alright. The minor of this location is the determinant of the remainder. I'm going to use this, and I just have to block out this and this, and then so we get negative 37. Alright, how about this location? Block it out. I'm going to use this row, block out that and that, and so I'm left with negative 37. Alright, so this one's going pretty good. Now this location, I'm going to use this one, and then it's going to block this out, and it's going to be 1. Hell yeah. Alright, so that was pretty decent. Okay, so now I'm going to find, and we're going to do it, all in one step. So so if I find the cofactor of this location, or if I'm trying to find the cofactor transposed of this location, it's going to be the cofactor of that location right there, because these switch places. So let's do that. The cofactor here is in a negative. So it's going to be the minor, but it's going to be negative. Do you think I can remember that? Probably not. But hell yeah. And then I'm going to use this. So I'm going to have 2. So the determinant of the remainder, we have a 2 now. So it's 2 times the cofactor of this location. There's no sign change on that location. You know what I mean? If I do this and I'm at one of the corners, there's going to be no sign change. Well, no. That's not true. I mean, we're just dealing with a 3 by 3. We're always taking a 4 by 4. First thing, we're going to a 3 by 3. Yes, all the diagonals will have no sign change. So that's, I've been kind of glossing over that. But hell yeah. So the cofactor of this location is going to be a positive. The minor of this location, but it's going to be 2 times the minor of this location. And then recall, we still have that -1 for whatever reason. Why the hell? Is because we're finding the cofactor of this location, and it's in it's the minor times -1. There you go. Hell yeah. You're going to use this row and column. So 2 times, I'm going to block that out and that out. So it's 2 times this. So I have -37 times 2, which is, alright, hell yeah. Alright, hell yeah, my battery died, and, oh yeah. And now I totally forget what the hell we were even doing. We were trying to find the cofactor transposed of that location, which is the cofactor of this location. It's going to be the minor times -1. Is going to be 2 times the determinant of the remainder, which is -37. And in my head, I want to be able to do this one really fast. You know, 35 and 35 is 70 plus 4 more. It's going to be -74. So that's 2 times -37 is -74, and with a sign change, +74. And that was this location transposed. So +74. There's no way this is, you know what I mean? It's just like that's a lot. That's a lot to do. You know what I mean? So hell yeah. Let's do this location. And where did that even go? You know what I mean? So let's do this location right away. So the cofactor transposed of this location is the cofactor of that. It's going to be negative. It's the minor of that location. Hell yeah. And it's going to be 0, so it doesn't really matter. Booyah. Okay, now where do we want to go? How about we go to here. So it's this value. And it's that value will be this value. So cool, we're going to, so this value is what I want to put, and it's the cofactor of this location. It's in a negative location, so it's the minor times -1. We have 1, and then we have 2 times -37. And then we have that same thing, and it's going to be +74. And that goes right, I'm glad I did that, because that was that location. The cofactor of this location is +74. Once we transpose it, it's going to pop up to that location. Okay, sweet. So now we're going to do, since we, see that's why I don't do this. Like, why the hell would you do this? Let's do this one. So this location is going to be a positive, and it's the, I'm sorry, let's do this location. No. If I take the cofactor of this location, it'll transpose to up there. Hell yeah. And it's going to be positive. Cofactor of this location, no, that's a tricky one. I'm going to take, because this is going to be 2 times the determinant of the remainder, plus this is in a negative location. So it's going to be 1 times -1 times the minor of that location. So sweet. So and then back to what are we doing? We're trying to find this value, which is the cofactor of this value. It's going to be positive because the diagonals, this is positive, negative, positive. So it's going to be the minor of this. I'm going to choose this row. Oh, see, that was dumb. Let's choose this row. No duh. Okay. So, which is just, and is a positive, so it's -37. I mean, it's in a positive location for the cofactor. So it's just the -37 times the minor of that row. The minor of that location. The minor of this location is crossing out row and column. And then you're just left with that. So we have negative 37. Let's do this one. Negative 37 times 2 times 2 minus 1 times 3. And for sure parentheses on that. So this is 2 times 2 minus 3. And then times negative 37. So that's 4 minus 3 is just 1. Negative 37. Now isn't this going to be a positive 37? Because, you know, I mean, after all of that, did we even forget, you know, I'm trying to find that value. Let's make a dot. And it's a positive value. So there is no sign change. So yes, negative 37. Brutal. But yeah, you can see why I like to take the minor first and then just easily swip the signs. But then I would have to rewrite all the numbers to get the cofactor transposed. But we're not even getting the, you know, it doesn't even look good. But we're going to continue anyway. So we're going to find this location, which is, it's a negative, you know, positive, positive, negative, positive, negative. And the cofactor of this. So yeah, this is a tricky one. I'm going to put a dot up here. I'm going to put a little negative sign, just so I don't forget that. And then we have, and this is a positive location, and this is a negative location for the cofactors of those locations. So we're going to have 2 times the determinant of this, you know what I mean, this times this, minus this times this. And then plus 1 times negative 1, however you want to think about that. It's this times the negative of that location. Times, you know, crossing that out and that out. 3 times negative 7 minus 1 times 4. So yeah, that's absolutely brutal. So let's do that with our calculator. Trying to find that location, which is the cofactor of this location. I'm going to go 2 times 2 times negative 7 minus 1 times 5. I mean, yeah, you're an absolute G if you're able to do this stuff. 1, I'd like to do it like this. 1 times negative 1. And then I'm going to cross that out and that out. That's what gets me. Sometimes I'll be like, I don't know what the hell I'm crossing out, but that and that. And then 3 and negative 7 minus 1 times 4. Cool. And that was the minor of this location, because that, you know what I mean, but I need to find the cofactor. It's just a negative. So we have positive 13. Whew. Okay, and, you know what I mean, we're getting closer. Let's keep with the diagonal thing. So, well, yeah, I actually just need to do this now, because it's getting a little rough. Okay, sweet. So there we go. Now, which diagonal location do we want to find? I want to find this value. So it should be that value, 3, 2. So the cofactor of that is going to be a negative. So I'm going to find this value, and it's going to be negative. It's going to be the minor of this location. I'm going to find the minor of this location and then put it right there with an up times negative 1. So that's what I'm doing. Minor of this location. I'm going to use this row. It's going to be 1 times, so this gets blocked, that gets blocked, that gets blocked. Oh, and we got zeros. So we are just money. Oh, and then what do you know? Like everything should be 0 that way. So let's do the harder ones first. What's the diagonal of this? If this is the diagonal, you know what I mean? We have dot, dot, and then so it would be here, here. So would this value go to there? Yes. It just crosses the diagonal. It doesn't flip. You know what I mean? So, hell yeah. So we're going to find, so I'm going to get this location. It's in a, it's a positive location. Whoops. Squeaker. Damn. Ate some food. Alright, so we have it's going to be positive, so it's just the minor of this location. Sweet. I'm going to use that column. So it's going to be 1 times, then I'm going to block out row and column. This is just the determinant of that. Negative 14 minus 5 is negative 19. Hell yeah. And it's good to be able to do a little bit of mental math. Okay, how about let's find this location. It is in a negative, so I'm going to find that location negative. I have to find the let's do this, the cofactor of this location. I'm just going to find the minor of this location and then multiply by a negative 1. I'm going to use this this column. And hell yeah. So it's going to be 1 times, going to block out that. So I'm just left with that 2 by 2. So it's just negative 7. But with the sign change, it's going to be positive 7. That goes right there. Hell yeah. And these should be 0. You know what I mean? The minor of this location, 3 zeros. Booyah. How about this location should be up there. So we're going to be the minor of this location, 3 zeros. Cool. This location should be up there. Minor of this, we got 3 zeros. When I say minor of this location, the minor of this location is the determinant of the remaining matrix. The determinant says pick a row or column and have the individual value multiplied by the minor of that, the cofactor of that value. Well, if you're taking 0 plus something, plus 0 plus something, plus 0 plus something, that's 0. So that's why you can do this. See, there's 3 zeros. Hell yeah, this value is going to be up there. So this location, hell yeah. So it's not, yeah, we got 3 zeros. So we got 0. And there you go. So we did it. This is the cofactor transposed to the upper, which again is it's the determinant of the upper times the inverse of the upper. So this is not the inverse of the upper. We would have to divide by the determinant. And the other way to think about that is like, this is nice numbers. If I divided it by kind of a big number, it'd all be fractiony. So I'm just mentally saying that that's helpful for me. Oh man, my camera's probably gonna die, or just overheat. We're into that zone. But now what we can do is we can check this. You know what I mean? And I'm not even going to do I said I was going to do this. I don't think so. I don't know. That was just brutal. I think we need to move on. We can do this if we made a mistake. Put it that way. Because what I want to do is take this upper and then multiply it by, this is technically like u. This is the inverse of u, but multiplied by a scalar. And so when we take an inverse times, if we take inverse u times u, we should just get the identity matrix, but it should be multiplied by a scalar. So again, we're going to get, you know what I mean, a bunch of zeros, and then what's our determinant over here? Our determinant was going to be negative 37. So we're going to get negative 37, negative 37, and then so hell yeah. So I want to find this location first. Multiply these two together, row and column. I see a lot of zeros, negative 37. Second one, you know what I mean? Row and column, 0, those are zeros, negative 37. So this is just really easy, row and column, zeros, zeros, negative 37. 2 zeros, sorry, fourth row, fourth column, bunch of zeros, negative 37. So we're good there. But still, you need to hit all those other values because you might have made a mistake. So we're going to hit those first. First row. So we have zeros on, so row and column. Got some zeros. Do we have some negatives? Yeah, just one. So it's going to be, 74 positive, and then 2 times negative 37 is negative 74. I didn't say that right, probably, but that's obviously 0. Let's move on. This value right here. Row and third column. First row, third column. At least I have a 0 at the end. A negative. I only have 2 negatives. The middle is positive. And yeah, we have that same thing. No, we don't. No. We have 2 times 74, and then basically 4 times 37. So visually, I can even see that playing around with these numbers. Cool. All right, this value. Hey, we got to do it all. You know what I mean? What negatives do I have? That's a negative. These are 2 negatives, so that's positive, and then negative. But we can just put it into our calculator. We got negative 37 times 4 plus 74 times 5 plus negative 37 times negative 7 plus 13 times negative 37. That's why it's useful to get used to. I mean, just today was groundbreaking. using the calculator like a keyboard. And hell yeah, we get 0. So that was pretty sweet. And that was that one. Okay, we're going to move on to this one. Second row, third column. We have a 0 and a 0 at the end. And then I visually see that. That's 0. All right, this one. 0 at the start. I see 4 times negative 37. No, I can't do it visually. Sorry about that. But I see 19 of these 37s, and then I see 4 of these 37s. That's going to be oh, and this is a positive. See, I should have done the negative first. So zeros, cool. So it's just going to be these ones. Yeah, I don't even see. I almost got confused. And then negatives, but this is positive. So I have 19 and 37. As my positive, and then these are both negatives. So I have a 5-pack of 37, and then a 14-pack of 37. That's what I can see that. So I can even do that one visually, just grouping groups of 37, knowing that this is 2 groups of 37. So negative 14 plus minus 5 is negative 19, which was positive 19 times 37. Hell yeah. If you could follow that, that's what I just did right there. Okay, so now we got this row but now I'm feeling really confident. And in this video, I didn't make any mistakes. But like I said, I spent 3 hours at the coffee shop trying to find all these mistakes and just realizing that these are your checkpoints. If I did find an inverse matrix, check it. Multiply it by the matrix, and you should get the identity. And we're just showing that I ain't dividing all these numbers by negative 37 because you get a ton of fractions. Cool. All right. So row 2, column 1. Row 2, column 1. Zeros, zeros. Okay. Row 3, column 1. Zeros, zeros. Yeah, this is just all zeros. Hell yeah. So column 2, row 3. Row 3, column 2. 0, 0, 0, 0. Cool. Row 4, column 2. Row 4, column 2, 0, 0, 0, 0. And then this one. So we did the easy ones last. Row 4, column 3. 0, 0, 0, 0. Hell yeah. So now I am totally confident that this is my gold. You know what I mean? This is my upper, the inverse of the upper times the determinant. This is the inverse of the lower times the determinant. And now we're ready to find the we're ready to, like, what's the equation on this? I mean, we had ax is equal to b. What are we trying to even do? We're trying to take a and make it into a lower and an upper. So now we have lower upper x is equal to b. Same thing, I need to take the inverse of both sides. So I need to take the inverse of lower and the upper. And then I should do the inverse lower upper and then put it right there. Because you have to do this in order. That's bizarre. I don't know if you can mix the order of those. No, you can't. And no, that was so funny. Because this is going to be a 4 by 4. And we're going to multiply it by a 1 by 4. You can't do the opposite. You can't take a 1 by 4 and multiply it by a 4 by 4. And we can just visually do that right away. I have 4 rows here, but they only have an x value. You know what I mean? This is just saying like 1x. 1x can't be equal to, you know what I mean? Like, So this second column dictates your variables. X, Y, Z, W. You know what I mean? And so you can't even do it that way. So that answered my question. So yeah, these inverses have to be out front. Now, what is the inverse of LU? Did we do this? Not in this video. Not in this video. We should go over the proof. So if I do have, and let's go over the whole thing so you can just kind of see it. If I have AX equals B, I want to turn A into lower upper X equals B. And then I want to take the inverse of both sides. I'm going to take the inverse of that times LU. X is equal to the inverse of that. See, this is just A. You can just see this is just inverse A times A, x is equal to inverse A times B. And this is just the identity times x is equal to inverse A times B, which is just the solution vector times this. And when you do those two matrices multiplied together, hell yeah, you get your right answer in the back of the book. Alright, so we're just saying that A is LU, and inverse A is LU inverse. Cool. And then we're going to take that to the both sides. Okay, hell yeah. And now, but what the hell is, do I just, if I multiplied L and U together, we have these, if I just multiply them together first, that's what this says. Multiply them together first and then take the inverse. That's literally inverse of A, which is, it's like what we're trying to find. So why did we take L and U? Because what we're going to say is that, I'm just going to say the proposition that, that inverse U times inverse L in this order is equal to, what is it going to be equal to? Is equal to, LU inverse. I'm going to say that. I'm going to say this is equal to this. And I probably shouldn't have wrote them in that order. Now, how can I prove that? And that's what I'm going to ponder for the next 5 seconds. Oh, yeah. This is an interesting one, and this is the only proof that I kind of know. You know what I mean? And I just ponder it and be like, okay, I get it. What they want to show is that they want to show this. They want to show LU times the inverse of LU is the identity matrix. And you can write it, in any order. Because we were writing it like, yeah, I kind of wrote it wrong anyway. So the proof is that if I have A inverse times A is equal to the identity matrix. What am I saying A is? I'm saying A is LU. Okay, so the first thing to do, the simplest thing, is to put this in parentheses. Treat it like an individual matrix, and then sub it into this equation. So we're going to do parentheses LU inverse times LU. And I'll put parentheses on both of them. Cool. Is equal to the identity matrix. What we're proposing is that LU inverse is U inverse L inverse. And I think, I'm trying to learn proofs, but I think this is, I don't know. I'm probably messing it up, but, because you could try it the other way. You could be like, hey, maybe I'm just going to propose that this is L inverse U inverse. And I can show that it is this one, and it's not that one. So I'm hoping that the inverse of LU after which is the inverse of A. This is the inverse of A. Is the inverse of U first times the inverse of L. Because I already solved for those. You know what I mean? If I multiply those two together in that order, inverse U times inverse L, I will get inverse A. That's all I have to do. I have the gold in my hand. This is U, inverse U. This is inverse L. Multiplied by scalars, so I just have to divide by the scalars, when I'm done. But that should be inverse A, and that's the gold that we're trying to find. Hell yeah. So this proof says, well, try it out. You know what I mean? If you want to sub that in, sub it in. If you're saying that, yes, this inverse A, it's in no better form here, it still sucks. But if you're saying it's these two matrices that you found multiplied in this order, try it out. So inverse U, inverse L, times LU. And now I can just kind of get rid of the parentheses. I can't change the order. Hell no. Matrices have to be, in a particular order. But now I'm going to see if this actually equals the identity matrix. I got rid of, well, we can keep the parentheses for the first go around. But the parentheses matrices are associative. So like, hey, this group is grouping up, that group's grouping up. Maybe both of the groups had a little fight, and hell yeah, these two want to group up. So that's what we're going to do. We're going to do inverse. We're just going to make them all individual first. Hell yeah. And then we're going to regroup. There you go. So we're going to do those first. And what is this? Okay, well, you know, I mean, I basically see inverse A, which is the identity matrix. I just see it with a different letter. So it's matrix, inverse of matrix L times matrix L. That's the identity matrix. So I'm gonna replace that. And so again, everyone comes to the party. No groups yet. But now I can know that the inverse times any matrix, inverse of U times the identity is just inverse of U. U times the identity is just U. And in any order. The identity times the inverse U is just inverse U. Identity times U is just U. So it doesn't even, with the inverse matrix, it doesn't even matter the order. But let's group these two together. Hell yeah. And that's just going to be U. So now we have this. Now our party is this. Hell yeah. And now we can see that, oh yeah, these two together is I. And so my brother was always like, well, I bet you if you work through the proofs enough, you will have that aha moment. And so this is my small aha moment. Don't know everything that's going on in the universe, but hell yeah, I feel pretty confident. And this was cool because it's just like, I just go from the approach of like, hey, let's just guess that it's in this order. I mean, I went through all the work to get these two things. Let's multiply them together and just assume that it's going to be the right thing. And we know that matrices can get multiplied together, but you can't just do this. This is a totally different value. And now we're going to show why that value sucks. So, and we got to get more light. All right, hell yeah. Yeah, I better get some more water too. All right, so we're gonna throw in the bad value and just so here's back up to this equation. I'm gonna say that this maybe it is just inverse L inverse U times LU is equal to the identity matrix. Again, everyone shows up at the party. No groups. You're going to do the grouping. All right, let's start grouping things up and finding something that makes halfway sense, and nothing does. If I group these together, cool. I have I have what I had at the beginning. That doesn't help. And if I group these together, well, I might as well have grouped those together. That don't help. So the only thing you could really group together would be the middle values, and that ain't helping. And you can't you can't multiply things out of order. So the inverse, I know nothing. So there you go. So we're kind of hit a wall. The other way came to a sweet spot. I can feel it. Hell yeah. All right, so now what does this tell us? It tells us, if we had to just remember what this tells us, it says the inverse of a matrix is inverse U times inverse L. Why? Is because the inverse of a because we said A is going to be the lower times upper, and the inverse of the lower times upper, that is the inverse of A, is equal to the inverse of the lower times upper, but this is going to be inverse U times inverse L in that order. That's what we're saying. And this is inverse A. So inverse A is equal to LU with the parentheses inverted, or the inverse of. I don't think you say the word invert. Hell yeah. All right, I think we're done with the proofity proofs, and now we can just find the inverse A. And once we find inverse A, we're going to get a 4x4 matrix. And all we have to do is multiply by the original matrix A. Hopefully I have that card somewhere. From the original problem. And when we do that, we'll get the identity matrix. So that'll still be a nice little check on reality. All right, so let's juice it out Where's our two little cards of gold? Let me go find them and get squared away. Alright, hell yeah. Cool. Alright, so here's our inverse upper, and here's our inverse lower. Now, there's a little catch. This isn't the inverse up. This isn't the inverse upper. This is the inverse upper times the determinant, times a scalar. We already found it. This is the inverse lower times the determinant. We can still multiply these, but they're going to be too high. By how much? Well, negative 432 times, and the determinant of this one is going to be negative 37. And is that the determinant of this? Yeah, the determinant of the upper is negative 37. And so I'm going to store that value as x. So we're going to be high 15,984. But that means, what the hell does that mean? That means that we're shooting for, when we multiply these two things to, I'm sorry. We're still trying to find the inverse of A. So this will give us the inverse of A, but it will be too high. Like this, what we're going to do, we're going to get the inverse of A times a scalar of 15,984. And then, so just keep that in mind. That's the only thing to keep in mind. We're going to get hella big numbers. We need to divide by 15,984 to actually get the inverse. Cool. So I can just say the inverse of A is 1 divided by this. You know what I mean? And then let's find the matrix. Alright, so, and I think it was useful to divvy this up. That seemed real useful. So we got 4 spots. And that doesn't, you know what I mean? You're going to do it in Excel where you can see the groupings. It's just interesting that not a lot of people actually do these little boxes for your matrix. Sometimes it might, I don't know, maybe it visually doesn't look as good than just numbers and space. Alright, booyah. Matrix multiplication. This row and this column. This is the hardest one, so let's juice it out. Negative 37 times negative 432. Already made a mistake. There you go. Plus 74 times negative 612. Plus negative 37 times negative 946. Plus 13 times 3802. Now I better double check. I don't really want to. I hate double checking, but yep. Cool. Alright, so we got our first value. Can we divide by x? Nah, not really, because these values suck. So anyway, so we have 55124. But once we get our first row, we can double check, because we still have, I mean, this is going to be the inverse of A. So I can take A, you know what I mean, and then multiply by the inverse of A. And what we should get in this value will be, once I do that matrix multiplication, this value, the first value, the A. Alright, hell yeah. So we're back. And, yep. Yeah. A times the inverse of A should give us an identity matrix. But because we're having it too high by negative 37 times negative 432, it'll give us the identity matrix times that scalar. So the diagonals will be that 5,000, or what's x? X is 15,984, and then all other values, after we multiply these two, the identity should be, it will be 0. Alright, cool. So let's just solve for these 3 and then do a double check. Because I don't know if I made a mistake. I was hoping to get 1 or 2 mistakes, but not very many, actually. Okay, second row, first column. I see some zeros, and we just got to go for it. Negative 37 times negative 612 plus 74 times negative 946 plus negative 19 times 3802. Cool. Negative 119598. Alright. Next one, 2, oh yeah, so we're getting kind of easier. Negative 37 times negative 946 plus 7 times 3802. Hell yeah. I remember this value, so that value is correct. Okay. And then we just have 3802. So, this video is also about, like, when can you check for mistakes? Right now. I mean, at least we can multiply these two rows and we should get that identity times that scalar. Okay, so we're going to take 5. Let's do this. So we got 1 times 55124 plus 2 times negative 119598 plus 3 times 61616 plus 4 times 3802. And guess what? Hell yeah. So we're all check OLOD. We're not getting the identity. We're not getting a 1. You know, if this matrix times this matrix is, the identity. We're not getting 1s here because these two determinants are scalars that are jacking these up by a value of 15,984. But at least we're on the road. Booyah. Okay, so now, and it's just multiplying matrices, but I think the killer is that you probably did make a mistake. Like today, I made a bunch of them, and it was just brutal going through and finding them. It can be an hour long. It can be hours, and you might not be able to find your mistake. And the worst thing about it is if you start from scratch, you're probably going to make that similar mistake. Because sometimes it's not. I mean, there's about 3 different types of mistakes. 1 is a negative sign. 2 is mathematical values. Like 3 times 9, maybe you thought it was 21. You know what I mean? Or something like that. Like adding, subtracting, confusing addition and multiplication happens a lot. The other is a theoretical problem where like you know what I mean? You thought F equals MA was 0 when the thing was moving. You know what I mean? Where you actually totally have a wrong concept. With this math stuff, it's a proposition. Like the first day I went through and thought the inverse of A was just, I was doing LU factorization. I got inverse L, you know what I mean? So let me show you this. If the whole thing is called LU factorization, where A is LU, well, inverse A, it seems like it should be this, but this slapped me in the face that was another 3 hour where I couldn't find my mistake. There was no mathematical, I found mathematical mistakes, and I combed through all those, but I was still getting something fundamentally wrong. And so then I went back to the proposition. And so people say, how should you study? Well, I don't know. If it's your first time, you do what everybody does, and you know what I mean. Take the integration of x squared, and you're going to go x to the 2 plus 1 divided by 2 plus 1. Do I even know graphically why to do that? Hell no. To this day, I don't know. You know what I mean? Or why even x squared, the derivative of x squared would be, you know what I mean, the first times the derivative of the second plus the second times the derivative of the first. You know what I mean? Can I graphically explain why the x squared is going to be, you know what I mean? This graph plus this graph. You know what I mean? Not really. Well, graphically I guess I could, because I'm going to add that and then that little chunk, and it's going to get me up. I'm going to add that little chunk and that little chunk, and I'm going to grow faster, you know what I mean? So I can kind of see that. So sure, I did. I just graphically showed you why if you chain rule x squared, the derivative of x squared, you're going to get the addition of 2x graphs. But I'm always looking for that stuff, you know what I mean? But I think you have to be a genius to find that type of stuff. But you don't have to be a genius to learn. Like, I just picked up the calculus book. Read the beginnings of books. Because you could have graduated from these subjects, and then you go back and read, like, the introduction, like any dynamics book. Like, I didn't even know what a rigid body was, you know what I mean? And that's kind of fascinating. It's just points on particles don't change, distance away. These two fingers don't change. They're the same distance. So technically this is a rigid body. My hand right now is a rigid body. That's the definition. Now, do teachers explain that on a daily? Hell no. You should go into class and be like, hey, this whole class is about rigid bodies. And so let's tell you what the hell a rigid body is every single day. You know what I mean? And just, you know, say it in different definitions. So that stuff gets hella lost. Alright, wrap it up. But, yeah, the calculus textbook. It says, yeah, everyone just does the problems and looks for the answers. The calculus textbook says, you should really spend your time going through the proofs of why something is why it is. And that is the gold. I mean, that's where I try to start all engineering problems, is from the proofs to the problems. And there's a couple different methodologies there. Like, I also try to employ the who cares, like, idea. And just like, hey, who cares? Like, what's the foundational basics of classical mechanics? You know what I mean? Not even labeling it, because heat, like thermodynamics, gets labeled. And it's just, hey, it's just mass moving. You know what I mean? Anyway, let's see how much juice we have left. Alright, hell yeah. No, we can do this. Okay, so moving on. Let's multiply some matrices. The not the funnest part. Row 2, column 2. See some zeros. And let's bust. Negative 37 times 36 plus 74 times 110 plus negative 19 plus negative 206. Hell yeah. And hopefully I do make a mistake because, well, I already did. I did row 2, column 2. So that's going to be that value right there. That was weird. And double check. Looking good. 6583. Okay, row 1, column 2. I was just going to say, and yeah, we have a 0. So yep. It's just good even, this is left-handed. I kind of like to work on skills like this. Is like, hey, let's do the number pad left-handed. Plus, so that would be these 3 fingers are going to be those keys. So it's going to be negative 37 times 110 plus row 1, column 2. Oh, yeah, and this is tripping me up. 7436, negative 37, 110. Yeah, 13. 13 times negative 206. Hell yeah. Negative 4084. Row 3, column 2. Sweet. See some zeros. And it's going to be negative, see, negative 37. Got to use this ring finger more. Times 110. Plus 7 times negative 206. Negative 5512. And hopefully we made a mistake. We probably didn't though, because we're doing pretty good. 206. Is there anything we can check here? Hell yeah. We have a column. Let's multiply it by that first row of this matrix. So we're going to do this. So we're going to have negative 4084 times 1 plus 2 times 6583 plus 3 times negative 5512 plus 4 times negative 206. Oh. See, and we should have got 0. You know what I mean? So maybe I just inputted them wrong, but this is the game. You know, you could make a mistake every 5 minutes. So this value, 2 times this value, 3 times that value, and then 4 times 206. Sweet. So we made a mistake. Hell yeah. So let's change some of these. So row 1, column 2. So I'm going to have those values. 74 times 36 plus negative 37 times 110 plus 13 times negative 206. Okay, that checks. Second one. Negative 37 times 36 plus 74 times 110 plus negative 19 times negative 206. Hell yeah. So there was our error. So this one was wrong. And we're going to go 2, 2. We don't have to work smarter, not harder. I'm going to store this as alpha A. Going to crank up to when we were trying to plug this in. And I'm going to replace... I shouldn't have done that. Well, it should just be this one. Yep. And then we're going to replace this value with alpha A. Hell yeah. Alright, so we're checked. Hell yeah, we made a small mistake. Wow, that took 5 minutes. So let's see how fast we can do kind of this next row. Oh, that's kind of nice to look at right there. Column 1. Hey, look at this. We just have 2 values. Negative 37 times negative 12 plus 7 times negative 60. 24. So yeah, that was... I have no idea. Row 1... See, I messed up. That sucks. No, we're good. Yeah, row 1, column 3 is this value. So negative 37 times negative 12. Yeah, but no, we did mess up. That happens to me all the time. So zeros, but it's these 2 values. Sometimes doing this a few times and then just spatially knowing where those values are. Look away and then look back at those values. Negative 37 times negative 12 plus 13 times negative 60. So we have negative 336. Second row, third column. Oh yeah, and we just got those values. So, hell yeah, look away, look back. 74 times negative 12 plus negative 19 times negative 60. I think the look away, look back is a really good strategy, especially with these numbers because it's overwhelming. Alright, third row, third column. So yes, these 2 values. Look away, look back. Hell yeah, negative 37 times negative 12 plus 7 times negative 60. That's the one was 24. Alright, fourth row, and it's just going to be negative 60. Alright, now we can double check this one. So these values should equal 0. Because they're going to equal the identity matrix, and if it's not a diagonal, everything else is 0. Negative 336 times 1 times negative 336 plus 2 times 252 plus 3 times 24 plus 4 times negative 60. And we put a 1 there. So hell yeah. So we're checked. Yeah, we did really good. And we got one more to do. First row, last column. Oh, this is easy. 13. 13 times negative 432. It's nice to end kind of on the easier one. Now it's just a nice little road home. Negative 19 times negative 432. 8208. Work smarter, not harder. This is going to be 7. I don't know. Doing things differently, though, can sometimes mess you up. So we're going to check this one, and then we'll be good. So we're going to check the multiplication of A inverse A. We now have inverse A. Congratulations. You know what I mean? Alright, so 1 times negative 5616 plus 2 times 8208 plus 3 times negative 3024 plus 4 times negative 432. And that's 0. Oh my goodness. So yeah, we hardly made any mistakes. Maybe just 1, maybe 2. Today I made hella. But what I wanted to show is where you can identify mistakes. I found my inverse A, and while I was finding the inverse A, I was double checking it, because why get too far? You know what I mean? This took 5 minutes a row, and I could have just checked after 1 row, but that's the minimum time that you can check if A inverse A is going to give you that identity matrix. Okay, so now, and we're not even done. Like, I feel like I'm done, but we have to go back to the problem statement. And the problem statement says, this is, get more time. So we have AX is equal to B. This is B. So I'm going to write B here. I'm going to write B is negative 10, 22, 2106, and negative 243. Okay, and what are we saying? I'm saying that this, the solution vector, is just inverse A times B. Cool. We found inverse A, kinda. We found inverse A, but too big. And so we need to do this. Like if I call what I found inverse A, I need to take inverse A divided by 15984. I'm going to say we found inverse A star. You know what I mean? We found inverse A times a scalar. But if I divide by that scalar, then I'm money. Hell yeah. And so, cool. So let's do it. So we're going to say, get another note card. Okay, so we're going to say this solution vector is equal to, where's our numbies? Okay, yeah, so we're done with this. This is the goal we can come back to, but this was up or lower. Multiplied by the determinants, don't forget that. What we're going to do is, and this was A, we're done with that too. This was inverse A. So we're going to say inverse A divided by, and I can even write this, divided by 15984. So this is matrix A divided by this number. Cool. We're going to multiply it by matrix B. And so I'm just going to get this over here. Negative 10, 22, 2106, negative 243. Alright, so, and then why does this work again? I mean, should we show why this works? The solution is going to be this matrix, which is, this is A star, inverse A star, divided by this. This thing is inverse A. Hell yeah. Times matrix B is going to be our solution matrix. So sweet. How do we multiply matrix? Row and column. Yeah, it's hella. I'm going to put this in my calculator as 15984, and then that's stored as X. So let's do it. Alright, so we're going to have 55124 times negative 10 plus negative 4084 times 22. And this is, I actually don't like the fact that it runs off the screen. It would be nice if, you know, I'll be looking for a calculator that, yeah, this calculator isn't like that. It does things that I don't want it to do. I wish I could just reprogram it, you know what I mean? And I don't want to, I mean, I'm so used to it though, but the things that I've been using, you know, if it goes off the screen, I can't check, and it's so slow to like go back and check. And so I think I am overdue for something, especially doing, yeah, I don't know. Yeah, it's fascinating. I don't like how it goes off the screen, because like right now I got to double check my work. That's all I'm saying. Hell yeah. Okay, sweet. And then we got negative 336 times 2106. See, it's already off the screen. Plus negative 5616 times, and if it wrapped around, I would be able to visually double check my answer real fast. Yes. So that is kind of a bummer. It's the industry standard, but it's too much. It costs too much. I mean, if you get it on a deal like 100 or less, or I get them at pawn shops, I found one for 30. But I think you probably just want to go for the higher, juicier technology. You get color. Yeah, I think there's, yep, it is definitely better. Okay, so just a I would consider this just a standard calculator. You know what I mean? But it's, if you're used to it like I am, I'm going to stick with it, I guess. Hell yeah. I hate, yeah, maybe I don't hate throwing things under the bus. I can't say I hate throwing things under the bus when I just throw things under the bus. You know, we do it, but it's okay. All right. So, and shoot. See, I need to double check what the hell I just did. Okay, hell yeah. And then so, Yeah. So our first value divided by x is just 1. Cool. So so check that out. If we had a, our solution x, this is our x value, y value, z, and w. So now we know that our x value is 1. Cool. All right, moving on. My camera's going to overheat in 30 seconds. Let's do this next one. So we have negative 119,598 times 22 plus 10722. See, I already messed up. Let's let the camera cool. Take a little breather. No, we got 30 minutes. Yeah. So we got negative 119598 times negative 10 plus 10722 times 22 plus 252 times 2106 plus 8208 times negative 243 divided by x. Hell yeah, we got negative 2. Booyah. And my camera is going to fry out. Alright, hell yeah. So we're back. And, yeah, this was kind of at the limit of using my vocal cords to do this video as well. So, man. Alright, so we're almost there. What are we doing? A, inverse A. Yeah, we got this. We had AX equals B. We're saying that the solution is inverse A times B. And this is inverse A star. And, yeah, and then we have to divide by that. But hell yeah. So cool. So this third value is row and column. So we have 61616 times negative 10 plus negative 5512 times 22 plus 24 times 2106 plus negative 3024 times negative 243. Divide by x. Hell yeah. So I guess we at least, well, I mean, this is satisfying, but will this, how do we do our double check? Because if we were saying this is A, and this is going to be our solution vector x, this times this has to be that as well. So that'll be our double check, and then we'll be done with the video. We got one more of these. So we have 3802. I don't know what I'm doing. 3802 times negative 10 plus negative 206 times 22 plus negative 60. Whoa. Times 2106 plus negative 432 times negative 243. Divide by x. Hell yeah, negative 4. Okay, and so now we're going to do a double check. I mean, we're done. We got the answer. Feeling pretty good about ourselves. We just want to check that these two matrices multiplied together are those values of B. And so we can even put, one of these papers back. So that was the value B. All right, so let's do these, and we're going to be done. So we have 1 times 1 plus 2 times negative 2 plus 3 times 3 plus 4 times negative 4. And that's going to be negative 10, so that jives. Hell yeah. Next row, 17 times 1 plus 22 times negative 2 plus 27 times 3 plus 8 times negative 4. Hell yeah, that jives. Alright, 2 more and we're done with this video. 7 times 1 plus 44 times negative 2 plus 47 times 3 plus negative 494. Times negative 4. Hell yeah. One more. Negative 10 times 1 plus 1 times negative 2 plus 7 times 3 plus 63 times negative 4. And hell yeah, so we did it. And we learned a bunch. We used lower upper factorization. Now again, we could have done this probably with Gaussian elimination way easier. I mean, honestly, we would have just been done. But the reason why you'd want to do this is because now here's our gold. This matrix divided by this scalar is the inverse of A. So if we have a system, some sort of physical system that requires this operation, and now I'm getting it because my nephew is like coding his own video games, and because I had to look up, it's just like, well, why? Well, one, I was just like, is a matrix just for equations? And no, it doesn't have to be just for equations. Like, it is equations, but it's also locations of things. It's changing orientations of things. And so for graphics, matrix can take pixels. That is equations. A vector of pixels, but then it can orient them differently. And so that still seems like equations, but it's different. It's kind of interesting. And that seems like an example where you could have this as your input. This could be, some sort of graphic. And then I want to, and then having it have this as your output. You might vary this. And so having this inverse, you can find the solution vectors of that. Cool. Alright, hell yeah, we're done with this one. Thanks for joining me. And it's fascinating I enjoy doing these kind of for the first time. It seems like everything that I do feels like it's for the first time. And it feels like they're 2-hour videos or whatnot. But, I don't know. I guess you could probably do this, without mistakes. I don't know, 20 minutes? 10 minutes? Like, what's the fastest? It's just fascinating that I made this video. Takes hella long. And the fact that you can kind of just do the same process. Even if you're just doing it with your calculator. But it is still a bunch of steps. We did all the steps to double check. Like, you don't have to. You could just assume that you didn't make mistakes. Get all the way to the end. And then that's going to be, if it works, it works. If it doesn't, it doesn't. And why wouldn't it work? Well, we could have had this be wrong. And if this was wrong, this, or inverse A, multiplied by B, will give you 4 wrong answers. But then you could take those 4 wrong answers, take A times those 4 wrong answers, and know that you're not going to get that again. So you could have done the double check right at the end. But for your first go-arounds, I suggest, and it's just kind of interesting to see how many locations in this problem can you do a check, just to make sure you can check your errors. Alright, we are seriously done. So the book that I enjoy this, Linear Algebra, this has a ton of mistakes in it. Not 10% mistakes, but not 1% mistakes. Maybe 1%. Like not a 0.1% mistake error, higher than that maybe. I don't know, it's kind of interesting. Maybe I'm, I don't know, out of 1,000, I don't know if there's 1,000 problems, in a chapter. But definitely you'll get mistakes every chapter and stuff. It's kind of fascinating. Yeah, I kind of like that too. The fact that they made mistakes. It makes you feel good when you can find textbooks mistakes. Anyway, hell yeah. It's just little things, little mishaps on numbers and things. But alright, sweet. So thanks for joining me. And that's a video. Booyah.